Hi, this is a lecture on t-tests for two related samples, otherwise known as dependent samples t-tests. It's also known as repeated measures t-tests because it's used in a repeated measures context, and also a within subjects designs. So you'll hear it called a within subjects t, or repeated measures t, and of course a dependent samples t. So the most common example of this is where we have one sample measured twice, creating two related samples. So example would be a pre-test versus a post-test. So you would test someone first as a baseline and then intervene with some sort of treatment, and then you would have a post-test. You can also create two related samples in other ways with dyads. And those dyads can be couples, twins, sibling dyads, figure skating partners, doubles tennis partners. I tried to provide an exhaustive list of possible dyads. And then you can also create two related samples using matching. So where one individual is matched on a characteristic of another individual in another sample. So based on IQ, you can match individuals on IQ, or age. That's another easy way of going about it. So two related samples can mean a couple of things. It can mean repeated measures across time, or two samples that are matched according to related characteristics, such as being a member of the same dyad, or matching according to some characteristics such as IQ or age. So how do we state our hypotheses in dependent samples T? For the null, we would say H sub O, or H subscript O. Mu, that's that Greek letter for mean, sub D, which refers to the difference, equals 0. For the alternative, we would state that H sub 1, mu sub D, does not equal 0. So this would be a non-directional hypothesis, in that we're not imposing a directionality in our stating our hypotheses. So what is this D again? The D is the difference score between x sub 2 minus x sub 1. So the two related samples, so husband and wife, tennis partner 1, tennis partner 2. So the difference in their scores. Or if they're matched on IQ, so the difference between one individual who has 100 IQ and another individual who has 100 IQ when it comes to X treatment outcome. So another way of thinking of it. So how do we calculate T for two related samples? It's the same basic structure for T as usual: sample statistic minus hypothesized population parameter, which would be whatever you state in your hypotheses. So in this case, it would be mu sub D equals 0, so the value of 0 would go there for the hypothesized population parameter over estimated standard error. With some slight adjustments, so the T would equal mean sub D, so the mean differences of D, minus mu sub D over SM sub D. So the minor adjustment, or a slight adjustment, is that you have this D value inserted in the notation. That D refers to the difference between the two related samples on whatever outcome variable you are testing. So what about estimating standard error? You estimate one standard error, as these are two related samples, versus if you were doing a two independent sample, or an independent samples T, you would have two standard errors which you would have to subsequently pull, etc., etc. But that's another lecture. But so you have one standard error, as these are two related samples. In calculating standard error, we need to think, well, what is our first step? Calculate the variance. And this is plain Jane variance, nothing to go crazy about. Sums of squares over n minus 1, or sums of squares over degrees of freedom. Now, degrees of freedom in the case of two related samples is n minus 1, because the samples are related, so it's treated as one big sample. Okay, so n minus 1. Now, independent samples T would be n minus 2, because they're two independent samples, so they'll be n minus 2. So variance is notated as sum of the square over degrees of freedom, or you can jump ahead to the standard deviation, which is S without the square mark, the square notation, which would indicate its variance, equals sums of square over degrees of freedom square root. And what's our second step to calculating the estimated standard error? It would then be to take that variance or standard deviation and divide it by n, and then take the square root. So if you took the variance s squared over n, then square root it, you would get the estimated standard error. Now conversely, you can use the standard deviation to calculate this estimated standard error by taking the standard deviation divided by the square root of n, and that would give you your estimated standard error also. So there's two ways to row in this scenario. You can take the variance to get your estimated standard error, or you can use the standard deviation and get your estimated standard error that way as well. So two ways. So let's do a hypothetical example. We have some patients who are phobic, meaning they are phobic of some object or item. There's n equals 7 of them. They are treated with imagination therapy. This is a little table that shows what happens when these patients are treated with imagination therapy. So we have, let's look, patient A through G. And so we have the time before imagination therapy in seconds that they're able to stand or be in the same place as their feared object. So let's say spiders. So patient A is confronted with a spider, and he can stand or she can stand that spider for 15 seconds. And then they're treated with imagination therapy, and meaning that they're told, well, imagine the spider is a fluffy bunny, or I don't know, something non-harmful or non-scary or whatever, or a puppy dog or whatever. And then let's see how long they can stand the feared object in seconds again. So after imagination therapy for patient A, they were able to stand the feared object of spiders for 24 seconds versus 15. So a gain of 9 seconds. 9 seconds more they were able to stand the feared object. And the D scores represent the difference, and they're all positive, so that means that there might be something to imagination therapy. It appears to consistently have a gain in seconds in terms of how long a person is able to stand their feared object. Okay. So next we have the D squared. If you square that value, the value for that, that'll come into play later when we do our computations for the dependent samples T. So what is our first step? We want to state our hypotheses. So for the null, we say H sub O mu sub D equals 0. That there is no change in phobia, being able to stand the phobia in seconds. For the alternative, we state H sub 1 mu sub D does not equal 0. That there is some sort of change. We're not specifying directionality, but based upon our review of the literature, we might want to specify directionality. So, depends. And in this case, we're going to set the alpha level at 0.01. So our second step is to locate the critical region. And in locating the critical region, we need to ask ourselves, is this a directional or non-directional test? And it's obviously non-directional. And then we ask ourselves, what is the level of significance? So we set it at alpha 0.01. Usually it's set at 0.05, but you can set it at what you want to set at, but at least be below 0.05, because that's just, rule of thumb. What are your degrees of freedom? So degrees of freedom in this case is n minus 1, because the two related samples are treated as if they are one big sample. And what is the T critical value? To find the T critical value, you need to actually look it up on a chart. And there are charts in field, but you can also find these charts in any statistics book or even online. They're widely accessible, these T critical value charts. You should have no problem finding one. But it's in your book also. So this is the one for the field book. And so we have N is 7. We have 7 patients. So N minus 1 is degrees of freedom. So that's a value of 6. Well, this is a two-tailed test because it's non-directional. And the alpha at 0.01, that gives us the T critical value of T equals T sub V, sub C sub V is 3.71. So this is the T critical value that our test statistic value needs to exceed in order to reject our null hypothesis. So next we're going to calculate our T statistic. Looking at the formula, we have some information already. Basically, for the mean sub D, you take the summation of D, which we have from the chart provided already, or table provided already from a couple slides ago. 56 divided by 7, which is the n, equals 8. So we have the mean sub D value of 8. So you can plug that in, mean sub D 8. Then we have the mu sub D value from our hypotheses, which would be 0. So 8 minus 0 is 8. So we have our numerator. Now the standard error, that's where things get sticky. To do that, we need to first know our sums of squares. And the sums of square calculation below is a summation of D squared minus summation of D squared parenthetically over n, which is 502, minus 56 squared over 7, which gives you an ultimate sums of square value of 54. So that's the number we're going to need to move forward with to calculate the standard error. Okay, so based upon that, let me get the drawing function ready. We have the 54 sums of square. Uh-oh. What is it doing? Okay, so we have the 54 sums of square. And how do we calculate variance? Variance is s squared equals sums of square over n minus 1. So variance in this case would be 54 over n minus 1, which is 6, right? Which would give us a value of 9. So 9 is our variance. And to get the standard deviation from that, we would take the square root of 9, which would give us 3, which would be our standard deviation, or just plain old S. Now, to get our standard error from that, you would take the value of, we can just do, well, we can do either one. Let's just go ahead and do 3. You take the value of 3 over, and what is n again? N is 7, and that would get you your estimated standard error, otherwise known as SM sub D. Okay, and then square root of 7 is 2.64, so 3 over 2.64 will give you the resulting estimated standard error of 1.13. So that will go in your denominator. So you have 8 minus 0, so you get the resulting 8, divided by 1.313, which gives you a t-test statistic of 7.08. T-test statistic of 7.08. That's pretty big, I would say. Well, let me erase this part real quick, and then turn off the drawing tool, and then we can go on to the next slide. Oh wait, so we calculate our T, which we just did, and it's 7.08. And now we have to make some decisions. So does our T statistic fall in the critical region? Yeah, most definitely, because remember we have a 7.08 T statistic value, and that's way above 3.71. So definitely. So we reject our null, that there is something going on with imagination therapy. And what does this mean in terms of efficacy of imagination therapy? I would say that it's probably pretty helpful. by and large. And of course, we want to be able to say how helpful it is. It's one thing to say, oh yeah, it's helpful, but how helpful? Should we be plunking money down into imagination therapy? Please note that this is hypothetical data, so don't start buying imagination therapy kits. So measuring effect size, we have the estimated D, which was the mean difference divided by the standard deviation. So for this example, it would be 8 divided by 3, which would give you a D value of 2.6. That's pretty huge. A D value of 2.6 is pretty huge. Basically, a D value of 0.2 is small, 0.5 I would say is moderate, and then anything above 0.8, a D value above 0.8 or larger is I would call pretty large and substantial. You can also calculate an R-squared. An R-squared is easily calculated if you have your T value. So it's 7.02. Well, mine was 7.08. Oh well, pretty close. Squared over 7.02 squared plus 6, which would give you a resulting R-squared value of 8.89. Or you could say that 89% of the variance and the dependent variable is accounted for by the IV. So IV being imagination therapy, and the DV is how long an individual is able to stand the phobic item. And this is actually a very large value of R-squared. So can we test directional hypotheses? Most definitely. For the null, we can say H sub O mu sub D is less than or equal to 0. So the amount of time they're able to stand a phobic item is not increased. Or we can, and then for the alternative, we can say H sub 1 mu sub D is greater than 0, meaning the amount of time is increased. So we can certainly do that. What are the benefits of related samples t-tests? Requires a fewer number of subjects because you're essentially measuring them twice in a repeated measures kind of context, or they're related in some way. So it's like you're doubling your sample size easily, and you can use a fewer number of subjects. Study changes over time. I think longitudinal analysis is quite interesting. It's one thing to look at someone at a snapshot in time in the cross-sectional approach, but to look at them across time is quite interesting. The only downfall of a T is that you can only look at it across 2 time points. And really, if you want to look at how people change across time, you want to look at more than 2 time points, because you want to look at not only the amount of change but the form of change. Because it's one thing to say that they've increased or decreased, but what is that form across time? What does it look like? Do they go up steeply at first and slow down? Is it quadratic, cubic, quartic, you name it? Anyway, that's another soapbox. But you can study changes over time. You can control for individual differences, such as IQ. You can say, well, I'm going to get somebody's baseline prior to treatment and then give them the treatment and then see the effect of treatment. So it allows you to control for these individual differences and makes your study much more rigorous. Disadvantages of related samples T. Outside factors can influence scores. Totally can influence scores. So you have to be careful and employ rigorous experimental design in order to make sure that these outside factors don't influence your scores. There's order effects, meaning in what order do you employ the treatment to some and then to others. So like is there an effect of when someone gets treatment? So like if they get the treatment of imagination therapy, does that automatically help them or affect their outcome? And it should affect their outcome, but is that really a function of the imagination therapy or having any kind of treatment? And so what some people will do, they will counterbalance it, or counterbalancing may fix this, is they'll give half the sample imagination therapy, then the other sample, other half they'll give, a placebo treatment, I guess, or whatever, to kind of counterbalance that to see, well, is it a factor of any kind of treatment? And please note the may is difficult to know always whether or not you're treating order effects successfully. Okay, well, that was a brief presentation on dependent samples T. Thanks.